Algorithms, let's talk about them. Matter of fact, I have yours right here. Oh, factorial. Why are you, some kind of traveling salesman? Hey there, my gorgeous friends on the internet, and welcome to this new series I'm starting called Data Structures and Algorithms. That's not an original name. The easy way? For beginners, they're all taken. So we'll start off quite simple. We're going to look at big O notation. And then from there on, we're going to look at different sorting algorithms that we can use, also different search algorithms. And then from there on, we'll look at linked lists as well, binary trees, hash maps, hash brownies, all of that good jazz. Okay, so let's get going. So let's have a look at big O notation. Before we write any code, let me just show you a quick drawing here that I just made. So these are houses, by the way, and this is the road here in the middle. So let's say we want to get to house number 7, all right? We're delivering food, all right? The programming didn't work out. So we are here at the beginning, right? Now, how would you approach this, right? You probably wouldn't go like house to house like this. You go to number 1 and be like, well, this is not 7, so I guess I'll go to the next one. So you go down here, that's 2, so I guess that's us. So I'll cross the street and go to the third one, right? You're incrementally going from house to house trying to find the number that you're looking for. So you get to 7, right? So that's one way of doing it, but there's different ways you can do it. Now, a better way we could approach this is that we already know that these houses are in order, right? So if I cross down the street, I know that the numbers are gonna get higher. So I could just maybe walk down to the middle of the street and then have a look in the back and see, oh, everything here in the back is probably not gonna be house number 7 because we're all in order, right? So house number 7 is gonna be from here on out forward, all right? So we can pretty much cut half of the size down right in the middle there and eliminate everything here on the left. Now, the first example might not be too bad of going house to house here in this case, because we're all just going to number 7, right? So at best, we're doing like a 10-minute cardio here, right? Not even that much amount. So let's say we get to a different neighborhood though, and there's many more houses here, all right? So this street has 1,000 houses on them, and we want to get to 800. Rent's super high in this neighborhood. So getting to 800 now is gonna take us much longer using the method that we use, right? Going from house to house to house. That's kind of like our algorithm that we used in real life. So getting to 800 now, going from 1 to 2 to 3 to 4 to 5 is gonna be much slower. So that's kind of what big O is. It's a way of mathematically kind of measuring the efficiency of an algorithm based on input size. So based on how your input grows. So if my input grows much bigger, if I have many more houses, will my algorithm be slower? So the example we saw with the houses where we went individually to each individual house is essentially linear search. So let's see how we can implement it in code, and then we're going to talk about the time complexity. So I'll do it in JavaScript and TypeScript. We might do it in Go as well, just for fun. So it would look something like this. So let's define a function here. Now let's call this linear search. Okay, and then here we're gonna have an array that this is gonna take in. Let's say it's gonna be a number array, and we'll also have a target, which is a number. And finally here, I wanna return a number. So if we just think about this a little bit, what we want is to go through each individual item in this array. And once we get to the target, we wanna stop and return it. Otherwise, don't. All right, so we can say something like for, we'll do a loop, we'll initialize a I, set it to 0, and then we'll say if I is smaller than array.length, right? So we're going through the array, then we can increment this by 1. So here we can say if the array I triple equals to the target, well, then we got it. So we can just return that I like that. If it doesn't find it, we can just return -1 at the end. And that's essentially it. So if we go down here and we do a linear search, and let's say I'll pass in an array here, 2, 3, 4, 5, just a bunch here, 12, 55, and then my target is gonna be 12. And since I'm returning the number here, we can also save it. So if I do Shift I can go to the beginning here. Let's save it in a constant, and I'll say, yay, this is my target element. Let's go down here at the bottom and do a console log yay and see if we get this. And that's essentially it. So if I go back here and console log this out for us, as you can see, we get back the number 7. Now that's the position of it because we ended up here returning just I. If you want to return the actual element, you can do array of I like that. And if we run this again, then we should get back 12. And there we go, we got back 12. So the time complexity for this algorithm will be O of n, where n here is going to be your data. So the bigger your data gets, the time for it to execute and operate will go linearly with the size of the data. So hypothetically, let's just say that this operation took a millisecond, right, to go through one of these elements. Well, then that would mean that it's 1 millisecond times n, right? So linearly. So if it's 10 elements in the array, then it would take 10 milliseconds. Now, you might be like, well, wait, what if my number is here? What if 12 is here, right, at the beginning? What if it's the first item, right? Then we don't have to go through everything, right, even if our data grows. But that's like assuming the best case scenario. When it comes to these algorithms, we usually tend to always want to look at the worst case scenarios, because yeah, the element that you might be looking for, 12 here, might be here at the beginning now, or you might get lucky and it's going to happen again, but eventually it's going to be somewhere at the end, and then it's going to run much slower. So that's why we say in the worst case scenario, the linear search here is going to be O of n. Okay, now let's look at something else. Let's say we have some users, all right? We managed to do it. We got Bob on board on our crappy website. We got Maria, we got John, and we got Pinocchio. Okay, cool. So what if I want to run a operation where I'm trying to access John, all right? I'm gonna go console log, and we'll go to users, and I'm gonna try to access the second index here. So this is something that you'd call constant time, which means that it doesn't matter how many elements we have here, all right? This can grow to 10 bajillion here. It doesn't matter, because what I'm doing here is I'm directly going to that specific user, all right? It's like having a GPS with the house and going directly to that location. I'm not checking what's happening before. I'm not checking what's happening after. I know where the address is, and we're gonna go to it. All right, so that's constant time. Now that doesn't mean that it's instant or anything like that. It just means that in this case, this is gonna take one operation to do. All right, there might be an example where it takes 3 or 4 operations to do. That doesn't mean that it's linear time now. That would still be constant time. For example, if I go here and do a for loop, so I say for let I, set that to 0, right? And I'll say I is smaller than let's say 3, like that, right? And then I'll do I plus plus. So I'm explicitly setting the value 3 here. If I do whatever it is I'm doing with the users here, console log users I, for example, what time complexity do you think this is? This is still current time complexity. It's not linear, because we are stopping at 3 here. So no matter, again, how big the data goes here, we can have 10 bajillion elements, we're stopping after 3. So even though we're doing 3 operations here we're just doing 1 operation, which we're reading one element of the array. What is this thing that keeps popping up? Here we're doing 3, but when it comes to constants, we don't really care. You know, we wouldn't say that this example here is an O of like 3. It took 3 operations to do something like that, or it's O of 1, all right? So if we look at constant time here on the chart, it doesn't really matter if it's 1 operation or 2 operations. All we really care about that this line stays pretty much flat here, and it doesn't increase our time complexity once the data grows. Now, other examples I can give you here is if we push something to the end of this array. So if we take users.push and we push in a new value here, let's console log this out. So we'll say users here. All right, let's just pop this open here and run this. So as you can see, we added the new value at the end there. So in this case, this is constant time as well, because we're just appending a value at the end. The whole array doesn't change in any way. However, if we try to shift or unshift a value here at the beginning, then we need to move every other element to the next location, right? So in this case, Bob here is going to have an index of 0, 1, 2, 3, 4. But if we add a new element here at the beginning, so if we insert something new, There we go. Now Bob is gonna need to go to the new position here to index 1, and then Maria needs to go from 1 to 2, and then John from 2 to 3. You see what I'm saying? Doing shift and unshift is an O of N. So we pretty much saw how linear search worked. Let me also show you how binary search works, because I kind of showed you in the initial example, right? Linear search was where we went from house to house to house until we reached the target. In this case, let's say 230. With binary search, what we did was we went down to the middle of the road and basically said, hey, anything before that could not be 230 because everything's sorted here, all right? So binary search only works on sorted arrays. So what we do is, let's say we're looking for 230, is we find the midpoint of this. So somewhere in this case, it would be, I don't know, let's say somewhere here, right? That's the midpoint of it, 174. I know it's not the exact midpoint, but whatever, it doesn't matter. So we check the midpoint of the array and we say, hey, is this the thing we're looking for? Is this 230? No? Okay, well, if it's not, we can eliminate everything before that because this number, 174, is lower than 230, so it cannot be any of the previous values. So we essentially cut this in half. And now what we can do is set our beginning point over to this next one. So 177 is going to be our new beginning. And now we'll cut it in half again. So the half would be maybe somewhere here, 264, right? 246. That's our new midpoint. Now we check again. Hey, is this bigger or lower than our value that we were looking for, 230? In this case, it's bigger. So it cannot be anything above this, right? So we essentially cut this to like this length right here. So then we check again, we put the midpoint again. And in our case, if the midpoint just hits, we keep doing this over and over again, slicing it in half and half until we have one element left. And that's gonna be our 230. So in code, to just make this a bit clearer, the implementation would look something like this. So let's define a function called binary search. And this is gonna take in an array. So we'll do the same. We'll say an array of numbers. And then we have our target as well. So the target is gonna be a number as well. And this is also gonna just return us a number here in the end. Okay, so what do we need? Well, we need to get our beginning point and the ending point of our array. So we can say let's say left side, or you can say beginning here, but I'll say left because this is going to be a bit easier. So that's going to be 0, right? That's going to be the first element in our array. And then the right, so I'll just define this, is going to be the length of the array. Okay, so we got that. So now we can do our loop. Let's do a while loop. We'll say while. And I'll say if left is smaller or equal than the right, which in this case it is, what we're gonna do is find that midpoint. So we can say const mid equals to, I'm gonna say math.floor, and we're gonna pass in the left plus right and divide all this by 2. So we'll say left plus right divided by 2. And now the first check we do is, well, if our midpoint is the target, then we're done, we finish. So we'll say if array mid, like that, triple equals to the target, then we can return array mid, like that. Now let's say our midpoint in this example is 195. So in case that this is smaller than our target, which is like 230, then our left here, right, our beginning, needs to be set a new value. We basically need to put everything else away here and set that as a new midpoint. So what we can do here is go here and say if array mid is smaller than target, right? What we want to do is left is equal to mid plus 1. All right, so basically our left side now will be put to the new middle spot. And I'm adding 1 to it because we already checked the middle, right? So let's say we checked 195 as a middle. Well, now the new left starting point should be 198, right? And then our middle is gonna be here somewhere now. And then of course we can do the opposite for the right. So I can just say else here because it's gonna catch it. I can say right equals to mid minus 1. All right, we'll do the opposite of it. And that's it. And finally here at the end, we can just return -1 if the target's not found. And let's give that a crack. So let's do a test here, and we're gonna say binary search. We're gonna pass down the houses as the array, and the second argument, let's say we're looking for 243 like that. Now check it out, I am also gonna console log out mid here in the binary search, and if we run this, now you're gonna see it only has like 4 or 5 operations that it needs to do to actually find that number. If we actually console log this out, so you can see console log out test, let's run this again, and you're gonna see that we do find the 243. So what's the time complexity for this algorithm? Well, we're essentially dividing it by 2 every single time, right? So we have 100, we divide it by 2. We're left with 50 divided by 2. We're left with 25 elements, we divide it by 2. And so on and so forth until we're left with 1 element. So this would be a O log of n. And if we view it on the chart here, as you can see, the bigger the data gets, this algorithm actually gets more and more efficient. Now I got a fun challenge for you, but before we do that, I want to challenge you to learn something new. And you can do that with today's sponsor, Brilliant. Brilliant is a learning platform where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and even AI. Now, we barely scratched the surface of these algorithms in this episode. That's why I want to highly recommend the Computer Science Fundamentals on Brilliant. They have over 43 interactive lessons here that cover everything from big O notation to sorting arrays to finding the best possible algorithm for your application. The best part is these lessons are short, interactive, and straight to the point. So whenever I have some downtime and I'm a bit unclear or I kind of forgot how an algorithm works, I love to jump onto Brilliant and do one of these interactive courses. I feel like it really solidifies your learning. So whether you're brushing up on fundamentals or diving into more advanced topics like data science, Brilliant makes it easy to learn anywhere, anytime. So give Brilliant a go by visiting the link in the description down below, or optionally you can even scan this QR code. And if you do, you get 30 days for free and also 20% off your annual subscription. So thank you so much for Brilliant for sponsoring this episode. Let's get back into it. Okay, so I want you to look at this code for just a little bit here and try to figure out what kind of time complexity it is. So we have a function, sum and max. I didn't type it out, but we got a 0 here for the sum, a max. And when you're looking for like trying to figure out the time complexity, the easiest way you're gonna actually see this is try to look for loops. All right, loops really give that away. So as you can see in this case, we have 2 loops. So we're going through once, adding the sum together here, and then we're doing it one more time down here to add the max as well, to find the maximum value. Okay, so what kind of time complexity is it here? Well, we learned that just doing a simple loop like that would be linear time, so O of n. So if we go down here, right, you'd represent this as O of n. But in this case, we have another loop. So we have 2 loops. So you could do, it's O of n plus n really, right? Or O of 2 of n. But when you have constants like this, like 2 times n or n plus n, again, we usually just ignore the constants. So you'd get rid of the 2 and just say O of n. So in this case, we don't say 2n, or even if you have like 10 plus n, right? We don't care about the constants here because they don't really affect it as much as something like O of like n squared. All right, the way this increases on the chart you're gonna see is way crazier. Now before I wrap this episode up, let me show you 2 other really popular time complexities that you might stumble upon. So one here is a function that it's called print all pairs. So what we're doing for is we have a loop here, as you can see, and then in there we have another loop. And as you can see, we're just matching array I and array J together here. So we're pretty much like trying to find all the different combinations we can pair these people together. Okay, that's kind of essentially it. So if we run this code here, let's run this, npm run dev. As you can see, those are all the possible different pairings that we can do. Now in this case, we are pairing the same people together here, but it is what it is, me, myself, and I, okay? Don't worry about it. So what's the time complexity here? Well, if we look at the outer loop here, this outer loop runs n times, so linear, right? However, the inner loop here runs n times as well. So for every element here that we loop over, we're doing another full loop. So in terms of complexity, this will be O of n times n, right? Which is n by the power of 2. How do you do the power here? Like that. O to the power of 2. So this would run in a quadratic time. Now last but not least, I wanted to show you one more example here. This might not make too much sense if you don't know recursion or stuff like that, but I wanted to show you an example of exponential time complexity as well. So this is about getting a Fibonacci number here. So as you can see, we're passing down the number, which is n, and we're checking our base case here is if n is smaller or equal than 1, then we return. That's when we stop, right? I added the console log here so we can see which Fibonacci sequence we're calculating. And then here we're returning, essentially we're calling the same function recursively with n minus 1 plus n minus 2. So we're calling this 2 times. So every time we run and invoke this function, it's gonna invoke 2 more of the same, right? So let's say we're passing down the Fibonacci number 5 here. So it would look something like this. When this gets invoked, it's gonna recursively invoke Fib4, Fib3, and Fib4 will invoke Fib3 and Fib2, and so on and so forth. And this is why it grows exponentially. So basically, if we run Fib2, the amount of calculations we need here would be 3, on 3, 5, on 4, 9, on 5, 15, and as you can see, it just keeps going up and up. And then as you can see, when you get to like 20, 30, the number just exponentially grows here. So essentially, every time we add +1 here to n, every time we add +1, we essentially double the amount of calculations that need to be done. So the way we could represent this would be O2 to the power of n. And it looks really, really crazy on the graph. So there we go, that's the gist of it. We'll cover much more in detail in the next episode, and if you want to see something specific, let me know down in the comments below. But thank you so much for being here with me and watching these episodes. Really appreciate it. Thank you for my wife as well, for also getting these really cool lights in the background. I really like them. She basically got me CSS background changer in real life. Don't believe me? Hey, change the background to big. See, I did it. How cool is that? All right, catch you in the next one. Bye.